Hi, this is Professor Fernandez. We are working on class notes D in lesson 7. So in this class notes, I'm going to introduce you to de Moivre's formula and also to the polar form of complex numbers and also to just visualizing complex numbers in general. So there's a lot that's going to happen in this class notes, but we will go through it fairly slowly. So this is one of the endpoints, right? I want to show that the complex formula z to the n equals z sub 0, where z and z sub 0 are complex numbers, that the solutions, in fact, there are n of them, are given by this formula. So there's a lot to digest here. So I'm going to, instead of do my usual thing, which is sort of explain what each term is, I'm basically going to ignore this formula for now because we are going to derive it, right? And you will see in the derivation why it ends up looking like this and what all these things mean, okay? So the first thing I want to do is talk about how we visualize complex numbers. So back in lesson 5 is when we first met complex numbers, and we did a lot of work in that lesson. So we saw that complex numbers have this form, z equals x plus iy, where x and y, and I forgot a d, where x and y are real numbers. Okay, so this is the form of a complex number. X and y are real numbers. So notice that, if I think about an example here, maybe like 2 plus 3i, I could visualize this in the following way. I could go to the xy plane and I could plot the point 2, 3. Okay? So this is one thing that you can always do. So we see that if we go back to the general form of the complex number, x plus iy, I can associate that with the point x comma y in the plane. That might be over here somewhere. So that's our sort of first result. Complex numbers can be visualized as points in the plane. Okay, so that's exactly what's going on over here. So that's really nice because we have a lot of geometry in the plane that we can now draw on by this correspondence. So let's go back then to the general form of a complex number, and let me just switch gears a little bit to a plus bi. All right, so if we go to our complex, if I go to our, I was about to say complex plane because there is exactly this correspondence. If we go to our plane and we plot the point a comma b, let's say a and b are positive so that it's up there, now we can do a lot of stuff. Okay, so what can we do? Well, I can choose to think of this point in at least 2 ways. Using what are called Cartesian coordinates. That's what I'm doing up here. That's what I did up here, right? I plotted the point 2, 3 by going 2 to the right and 3 up. Those are, Cartesian coordinates. Or I can choose to think of the point AB down here in a different way, using what's called polar coordinates. So if I have the same exact point, A comma B, there's A and there's B. Okay, I'm going to zoom in here. Okay, so what can I do? Well, I can, instead of thinking of this as go to the right A units and then go up B units, what I'm going to do is I'm going to say, you know what, I'm going to think of this as go to the start at the origin. Oops, that's the eraser. Start at the origin and then go A units away from the origin, right? And then go some angle theta up from the x-axis until you get to the same point A comma B. So I will erase all that and then just draw the red line that results. Okay, so this was some angle theta from the x-axis. All right, so zooming back out here. If I do that, that's a very fundamentally different way of thinking about how I get to the point AB. And I'm going to call the distance that I got, that it took to get from the origin to that point, r. Okay, so then what do I know about r? Well, I'm going to pop out this image here and notice that there is a right triangle here, right? So the R, the hypotenuse of this right triangle is R, the base length is A, and the height is B, right? So this is B, this is A, this is R, and this is theta. And then this is an illustration of exactly what I was saying earlier. Now that we're in the plane, we have all this geometry that we know and love that we can use. In particular, we have some trigonometry that we can use here. So I can say that, let's look at all the ratios. Cosine of theta is the adjacent over hypotenuse. Sine of theta is the opposite over hypotenuse. And then tangent of theta is the opposite over adjacent. All right, so let me solve this. I'm going to call this equation A and call this equation B. So let me solve equation A for little a. So I'm going to multiply by R. And then solve equation B for little b. I'm going to multiply by R. Okay, so what's one thing that I noticed? Well, remember where all of this started, most recently at least. It started up here, right? So I had represented Z as A plus BI, and then I went over here, I represented it as a point in the plane, and then I started thinking of it differently, and not in Cartesian coordinates, but in terms of how far away from the origin is this point, and what is its angle with respect to the x-axis. Okay, so that's where this all started. And now I've gotten to a point where I've made a very interesting discovery. If you know R and theta, then you can put them in here and they will give you back the A and B values. All right, so this is effectively the transformation from Cartesian coordinates to polar coordinates. So what I'm going to do is I'm going to go back to this Z here, and I'm going to say Z equals A plus BI. I'm going to substitute in the A, which is R cosine theta. I'm going to substitute in the B, R sine theta, times I. And then I'm going to notice that both of these have an R, so I'm going to factor that out, and then be left with cosine theta plus I sine theta. Okay, so far so good. I'm just going to erase while that sinks in a little bit, because I claim that you have seen the thing in parentheses before in this course. So if you can think back to some other lesson or some other concept that you've learned in this course, hopefully you can remember what that thing in parentheses is. It's a very famous expression. So I'm going to tell you what it is right now. So this is from lesson 5. We'll go back to lesson 5 to refresh your memory. E to the I theta, right? This is Euler's formula. So what we have just shown is that if I start off with a complex number written out in the usual form that we introduced it in lesson 5, I can write it in a different form, which has the form R e to the I theta. And, again, this is, as we just derived, a reflection of the fact that we can transform in the plane the point, oops, I did not want to do that. So maybe over here. So bear with me while I get back to lesson 7. I think I might be close. So anyway, what we've just done is a reflection of the fact that we can transform the points in the plane A comma B into the same representation, the same point AB, just represented in terms of R and theta. Right, so I will draw up that picture once again. So here's my point AB, represented in terms of how far away it is from the origin and the angle with respect to the positive x-axis that it takes to get there. All right, so remember that A was R cosine theta, B was R sine theta, and tangent theta was B over A. Okay. So what I'm going to do now is I'm going to take these two equations and I'm going to square them, and I'm going to add them. Okay. So a squared plus b squared equals r cosine theta squared plus r sine theta squared. You might be wondering, why am I doing this? I'm doing this because we have a relationship that transforms a and b, um, or decomposes a and b into r and theta, but we kind of, need to go the other way for the purposes of what we're trying to do here in this lesson. That is, if I know a and b, I want to be able to write down r and theta. So I kind of want a relationship that's inverse to this, right? I don't want to know r and theta and then be able to write down a and b, which is what this relationship would be really, really good for. So I'm deriving now the next couple of equations that are going to give us those ways to figure out r and theta from a and b. All right, so back down here, so this is r squared cosine squared theta plus r squared sine squared theta. Factor out the r squared, left with cosine squared theta plus sine squared theta, and that's equal to 1. So just left with r squared. So now I have a relationship between a and b that involves r. Excuse me. Again, based on the geometry, you might have already predicted this. If I go back up here, remember that in this right triangle, the base is a, the height is b, and the hypotenuse is r. So this is nothing other than the Pythagorean theorem, right? I just wanted to get at it a different way to show you how this transformation actually connects with that geometry. Great, so then I'm going to write down some other relationships here, which is kind of the inverse of the red ones. So we have found that r squared equals a squared plus b squared. Okay, so this is this is the principal way to find the r value. So as an example, suppose that z equals 1 plus 4i. So then if I want to write out the polar representation, which is what this is called, of this complex number, the first thing I would do is I would find r. I would say r squared equals 1 squared plus 4 squared, right? A squared plus b squared. And that's 17. And then I would take the square root of that, and that is my r value. So I can start off saying, oh, the polar representation is square root of 17 e to the I theta. Okay, so all that's left to do now is to figure out how to find this theta value. So that's the next thing we're going to do. And that one, actually, we've already written down a formula for. Okay, so that is what's over here on the right-hand side. That's this tangent theta equals b over a. So one thing to know about this is that, to find theta from here, we need to take the inverse tangent, the arctangent of b over a. A lot of things to know about this. If a is 0, right, then that's going to be a problem. We can't divide by 0. So, but if a is 0, if you go back to the representation, that means that the point AB we're looking at is either on the positive y-axis, on the negative y-axis, or is the origin, right? And the origin we're not going to want to represent in polar form because r equals 0. So if the point is on the positive y-axis, then it's an angle of 90 degrees from the positive x-axis. If the point is on the negative y-axis, we have to go all the way down here. That's 270 degrees, right? So that's 3 pi over 2. So again, this formula that we derived is useful, but there are going to be instances where you'll have to use a little bit of your knowledge of the geometry of the situation. The second thing I'll mention is when you find values for arctangent, right? Again, keep the quadrant in mind. So it might be easier to visualize, as I've done here, where the point is first, and then use the arctangent formula to give you the theta value, and just make sure that everything lines up. Because again, for some a values or for other values, you might need some more information than just plugging in the a and b values into the arctangent formula and having it spit out a theta value. All right, so I'm going to leave in red here the two principal equations that we are going to use to find the r value and the theta value. And now that we have discussed that, we know how to find r, we know how to find theta. we know how to do this. We know how to take a complex number written in the standard form, a plus bi, and write it in this polar form. Great. So believe it or not, we are not done, but we're going to be done in probably 2 minutes because now we're going to do everything that we actually wanted to do in this, well, I should say the second part of what we wanted to do in this lesson notes. We want to talk about de Moivre's formula. Okay. So now that we can visualize complex numbers, we can understand them as points in the plane, but also this polar form. De Moivre's formula is going to be next. So de Moivre's formula helps us to find solutions to the complex equation z to the n equals z sub 0. So let's go back up here. So this is what we're going to do now, and we will derive this formula. All right, so what do? Well, the first thing I want to say is if I have the complex equation z to the n equals z sub 0, where I am assuming there are n, where I'm assuming that n is an integer, right? So I'm thinking about maybe like z squared, positive integer, z squared equals z sub 0, or maybe z cubed equals z sub 0, something like that. Excuse me. Then to find solutions to this equation, you might think, naively that I'm just going to, take the, nth root of everything. And this will give me z equals nth root of z sub 0. That turns out to be one of the possibilities. But, if n is like 10, for example, I will get like the 10th root of some complex number. And it seems like I only get one complex solution when in fact there should be a ton. Actually, there should be exactly n. That's what the fundamental theorem of algebra tells us. So if I just do this process of taking the nth root, I am not going to obtain all of the solutions that I should obtain. So this is part of what de Moivre's formula helps us to figure out. What are those other solutions? Excuse me. And that explains, is a little preview of why this range for k is there. Okay, so with that quick little preview, introduction, how do we figure this out? So let's write out z to the n equals z sub 0. And the first thing I'm going to do is I'm going to follow what's here. So step number 1 is to decompose z sub 0 into its polar form. So that's exactly why we just talked about all that stuff a few minutes ago. All right. So again, what we would do to do that is we would take the z sub 0 in its not polar form, and we would figure out the r value, and we would figure out the theta value. Again, I'll just write it here so you remember, using the Cartesian plots to help you, have some more confidence that the theta value you find is in fact the theta value for that corresponds to the Cartesian expression of the point. All right, so I'll put a theta sub 0 here to remind you that this is theta sub 0 and r sub 0. This goes with z sub 0. Great, so step one right here. Decompose z sub 0 into its polar form. Great, so step 2, what do? So because we are solving z to the n equals z sub 0, we are now solving z to the n equals r sub 0 e to the I theta sub 0. Excuse me. So this is the point where, again, you are instinctually wanting to take the nth root. And we are almost going to do that, except I'm going to point out a freedom that you might not have noticed yet, because I've been saving it for this particular point. So when I determine the theta value for one of these points in the plane, let's say the point like 1, 5, okay? And whatever the theta value is there, I won't calculate it. It's the same theta value as if I added 2 pi to it. So this is theta plus 2 pi. It's the same theta value as if I added, went around, twice. So this is theta plus 4 pi. Okay? And this is all going around in the positive direction. It's exactly the same if I went around in the negative direction, okay? Or twice in the negative direction. Right? So I have a lot of freedom and multiplicity in the actual angle, right? This is like saying 0 degrees is the same as 360 degrees, same as 720 degrees, same as negative 360 degrees. So I'm going to build in that freedom into this exponent here, and you'll see why in a minute. Long story short, this is going to help us understand this part of de Moivre's formula. Okay, so I'm going to build in that freedom by saying that this theta value is actually theta plus 2 pi k, okay, where k is an integer. Okay, so that's a mathematical expression of exactly what we were talking about. If k is 0, then this angle is the original angle that represents the point a plus bi. If k is 1, then this is theta plus 2 pi. So that's going around one full rotation and ending up at the same angle theta sub 0, just counted plus 360. If k is negative 1, then it's theta sub 0 minus 2 pi. Same thing, you go around the opposite direction, but you end up at the same theta sub 0 place. So that is why we can write that there without changing the equation. Okay, and then once I have that freedom, I say, okay, I want to solve for z. So now I am going to take the nth root of both sides. So nth root of r sub 0, e to the I, theta 0 plus 2 pi k, and then the nth root of this. So this looks kind of complicated and scary, but that's okay, because this nth root is just going to divide the exponent. So this is e to the I, and I have theta sub 0 plus 2 pi k over n. Okay. All right, so now I am very, very close. Let's see if I can move this, sort of. Took the parentheses with it. So now I am very, very close to the final form of my de Moivre formula. I have to notice here, to get my final form, integer, that I wanted n solutions. Again, that's the fundamental theorem of algebra. That tells us how many solutions this equation up here should have. Should have exactly n. But down here, k is any integer. There are an infinite number of integers. So it seems like I've gotten an infinite number of solutions, right? Because I can substitute whatever k I want. But this is where we got to realize the geometry of the situation. So let me start writing out some of these solutions. So I'm at this point going to denote them as z sub k, because you give me a k value, that's an integer, and this formula pops out a z value. So what I'm going to do then is start writing out some of these z values. Excuse me. And let me start with 0. K is an integer, so 0 is an integer. Z sub 0, nth root of r sub 0 times e to the I. Okay, if k is 0, then I just have theta 0 over n. Fine. And then let me write out z sub 1. So this is going to be nth root of r sub 0, e to the I. So here k is 1. So I have theta 0 plus 2 pi over n. All right, and then let's keep going. What about z sub 2? Z sub 2, let me draw a line here so you can distinguish, separate these in your mind. z2, r sub 0, nth root of r sub 0, e to the I, theta sub 0 plus 2 times 2 pi over n. All right, if I keep writing out these roots, let's see what happens when I get to z sub n. So it's going to be nth roots of r sub 0, e to the I, theta sub 0 plus 2 pi times n, right? Again, here, this is my k value, so that goes right here. So I'm multiplying by n over here. Okay, so 2 pi times n all over n. And now notice that this simplifies. This is nth root of r sub 0, e to the I theta over n, times e to the 2 pi I. Right, 2 pi I, because these n's go away. Okay, so I'm going to focus here on this term. So what happens? I'm going to scroll up to give myself some space. E to the 2 pi I. Remember Euler's formula, which said that e to the ix is cosine of x plus I sine of x. All right. And then remembering your trigonometry values, cosine of 2 pi, this is cosine of 360 degrees. That's 1. Sine of 2 pi, that's the y value on the unit circle at 360 degrees. That's 0. So e to the 2 pi I is 1. So if I go down to the formula right here, this last quantity over here is nth root of r0 e to the I theta 0 over n. So what has happened? What's happened is that the recap is I started here. I wrote this in the polar form, and I have just derived a formula for the solutions that looks like this. Now, I originally had that k was an integer, and that produced an infinite number of solutions. But now that I've started writing them out, I started with z sub 0, and I got that one. And then I wrote z1, and then I kept going. And now that I wrote zn, I noticed that I get back to the z sub 0 solution. Okay. So you'll explore some of the geometry of what's going on here in the capstone that's coming up. But at least for now, notice that when I let k equals n, I duplicate this solution here. The long story short of why that's happening is because of the angle, right? Every time I am taking the angle theta 0 and I'm adding literally a multiple of 2 pi over n, all right? So I'm starting with the angle, I should say, theta sub 0 over n, and I'm adding a multiple of 2 pi over n. After I add n of these, I add 2 pi, and that's exactly what happened here. I added n of those 2 pi k over n's, and I get back to exactly the same angle. So long story short, what this tells me is that if I if I were to continue writing down like z sub n plus 1, z sub n plus 2, I would start duplicating all of these roots. Okay, so I don't get new solutions out of all the infinite number of solutions that are out down here. So instead of letting k be an integer, so that in order for me not to duplicate all these solutions, I should stop writing k's at n minus 1. Okay, you might wonder, what about the negatives? Like, what if k is negative 1? Okay, so that's kind of like the same thing that we did, just in reverse. So if k is negative 1, right, look at what's happening up here. It'd be theta 0 minus 2 pi k over n. Oops. Yeah, I'll just do it this way. If k is negative, then it's kind of like if I replace k with negative k, right? So here's the minus sign here. So when you look at this angle, what you're doing is you're taking the original angle, and then you are subtracting multiples of 2 pi over n. Okay, kind of like what we were doing here is we were taking the original angle and we were adding multiples of 2 pi over n. So geometrically speaking, in this scenario, wherever the point was, and you had a theta sub 0 angle that corresponded to it, you were kind of like adding multiples of 2 pi over n. And then eventually you get back to the same place. In this scenario over here, and notice what I just did there is I went this way, counterclockwise, right? Because we're adding multiples of 2 pi over n. In this scenario over here, you start off with the same point, and you start off with the same theta sub 0, but now you subtract multiples of 2 pi over n. So you would go this way, right? When you subtract angles, or when you add negative angles, you go clockwise. So at some point, you're going to land back to exactly where you are. So the grand conclusion of this analysis is that out of the infinite number of k values, right? The infinite number of integers that k could be. We really do not need most of them, right? We don't need most of them. These are all the k values that we need. To generate the n, there are n k values here, the n unique solutions to the problem z to the n equals z sub 0. All right, so that yields exactly, if I just declutter everything here and move this down here, that yields exactly the de Moivre formula. So that's what this is. Okay, so that's it for this video. Thanks for sticking around.